Welcome everybody to Algebra 2, Section 4.2, Solving Quadratics by Factoring. So we have 4 steps we're going to follow, and really 3 because I'm going to not have us do this 4th step here. So the first step is to move all the terms to one side and set the equation equal to 0. Eventually we want this into standard form, which remember standard form is ax squared plus bx plus c. It's possible we won't have a bx term and sometimes we'll have a c term. We'll always have an ax squared term. Then we'll factor, and then we'll set each factor equal to 0 and solve for each x value. So solve each equation by factoring. Number 1, and we notice this whole first page is already equal to 0. It's already in standard form. So we always check for a GCF first when we factor, and then we progress to different things from there depending on the number of terms. But here we look for a GCF. There is the GCF of x, and then we're left with x plus 9 equals 0. Now this inside the parentheses is fully factored. So now what we do is we set each of these factors equal to 0. And the reason why we're able to do that is because we can say that, hey, because x times this equals 0, we know that anything times 0 equals 0. And the only way to multiply and get 0 is if 0 is involved. We can't take like 5 times 2 and get 0, for example. 0 would have to be one of the numbers being multiplied. And because 0 would have to be at least one of the numbers being multiplied, if not both or all, that means that either this is 0, or both are 0. And so what we do is we say, okay, if x is 0, that would make the equation true. Or if x plus 9 is 0, it would make the equation true. Because then you'd have 0 times x plus 9 would be 0, which is true. Or you have x times 0 equals 0, which also would be true. So we set up both these equations for each of those scenarios. Then this first one we say is already solved, so x equals 0. Second one we subtract 9 and get x equals negative 9. And so if x was 0 or negative 9, it would make this equation true because you would have 0 times something or something times 0. And though either one of those would equal 0. So that means these are the two solutions. And if you plugged 0 back into both of these x's, you would get 0 plus 0 equals 0. And if you plug in negative 9 back into both these, you'd get 81 plus a negative 81, which would also equal 0. On to number 2, we will once again make sure it's in standard form, set equal to 0. It is in fact. So we go ahead and look for a GCF. There is one, it's 4x. So we factor out 4x, and we're left with x minus 2. Inside the parentheses, there's no more factoring we can do with x minus 2, so we go ahead and say 4x equals 0, x minus 2 equals 0, and we solve each of these. The first one we solve by dividing by 4, and we get x equals 0. Second one we solve again by adding 2, and get x equals 2. And 0 and 2 are the two answers. Next, we'll look at number 3. We look to make sure it's in standard form. It is. We look for a GCF. There is none. So when there's two terms, we want to look for a difference of two squares. And so we say this is in fact a difference. There are two things, and they are both perfect squares. X times x is x squared, and 2 times 2 is 4. So we can make two parentheses, where we have x and x to start, because x is at the beginning, and 2 and 2 at the end, because 2 is at the end, and 1 is subtracting and 1 is adding, in either particular order. And that equals 0. And now that these are fully factored, we have x minus 2 equals 0, and x plus 2 equals 0. We set each factor, everything that's multiplying, equal to 0. Solving these by adding 2 and subtracting 2, we get x equals 2, and x equals negative 2. When you get the same number, both just positive and negative versions of the number, you could choose to write it like this as well. It just says both positive and negative 2. And that is truly two numbers, but written as if it's 1 almost, but this means positive or negative or plus or minus 2. Looking at an example 4 here, we make sure it's in standard form. It is. We look for two terms and say, hey, okay, well, look for a difference of two squares. It's a difference. There's two things. They are both perfect squares. 3x times 3x is 9x squared, and 5 times 5 is 25. So we have 3x minus 5 times 3x plus 5 equals 0. From there, we set each of these equations equal to 0, and we solve. So this first one, I solve it by adding 5, dividing by 3, and I get 5/3. Second one I solve by subtracting 5, dividing by 3, and I get negative 5/3, which, as we mentioned with the last problem, you could write as x equals plus or minus positive negative 5/3. And either one is saying the answer. Number 5, make sure it's in standard form. It is, in fact. There is no GCF, but we look for one. There are 3 terms. When we have 3 terms, we look to make the x. Then we do a times c. 1 times 21 is 21. B on the bottom is negative 10. And we look to find 2 numbers that can multiply to 21 while adding up to negative 10. The results are negative 3 and negative 7 in either particular order, as long as both are negative. And because a is 1, we can do a shortcut. We can do x minus 3 and x minus 7 equals 0. We always just do the variable x without the square, because x times x will create the square. And then we take these from the sides of our x. Then we set each of these equal to 0 and make our 2 equations, or make the equations from the factors. And we now say, okay, if we add 3, we get x equals 3. If we add 7, we get x equals 7. And so we get 3 and 7 as our 2 answers. Number 6, we say that it is in standard form. Double check for it though. Then we look for a GCF. There is one. The GCF is 2. Then we have x squared minus x minus 12. And I'm really happy that we caught the GCF here, because by doing so, we made it so our a is 1, which is going to allow us to use our shortcut after we make the x, as well as making the numbers in our x smaller to make our life a little bit easier. So the top 1 times negative 12 is negative 12, and at the bottom is going to be the number negative 1. So 2 numbers that would multiply to negative 12 but add up to negative 1 would end up being negative 4 and positive 3. And you can do the positive 3 first and negative 4 second, as long as the 4 is negative and the 3 is positive, so they add up to negative 1. So we have 2 times x minus 4 times x plus 3. We were once again able to do the shortcut because it's the 1x squared after we take the 2 out as the GCF. So we set each of these equal to 0, including the 2 for a moment. If my pencil doesn't glitch on me. And as we set each of these equal to 0, we can look at this first one and say, okay, well, 2 can't equal 0. So we move on from that one and disregard it. Then we add 4 and get x equals 4. Subtract 3 and get x equals negative 3. And those are the answers. Now, I do want to note, it is actually something you could do at the very beginning of this problem. It's where you take this, 2x squared minus 2x minus 24 equals 0. And if you notice they all have a GCF of 2, you can divide by that GCF of 2 since it doesn't involve a variable. If it does, you can't do this. But you can divide everything by the GCF of 2 and get x squared minus x minus 12 equals 0. And then at this point, you don't end up having to worry about this GCF of 2 out here. You just continue factoring the same way we did from inside the parentheses. And so we just get as if this never existed. You could also do that same exact task right here between the pink and the blue, where you divide everything by 2 right here and have those reduce, and you're left with this equals 0. Moving on to example 7. 7, we make sure it's in standard form. It is. We check for a GCF. There unfortunately is not one. So a times c is negative 90. B on the bottom is negative 13. Then the 2 numbers that work are negative 18, positive 5. No shortcut here because a is not 1, so we get 3x, see I wrote cubed, but 3x squared minus 18x plus 5x minus 30. So then we put the first 2 in parentheses, last 2 in parentheses. Oop, I forgot to have it equal to 0. And then the first 2 have a GCF of 3x, and we're left with x minus 6. Last 2 have a GCF of positive 5, and we're left with x minus 6 again. Those are the same, which they should be, otherwise that means we made a mistake. And so we put the same parenthesis the same in one parenthesis, the x minus 6, and kind of the leftovers for my slang there in the other parentheses at 3x plus 5. Then we end up setting each of these equal to 0. And as we set them each equal to 0, we get x equals 6, as well as x equals negative 5 over 3 once we subtract by 5 and divide by 3. And those are the two answers. Moving on to number 8. We make sure it's in standard form. It is. We look for a GCF. There is not one. So we have a times c is negative 24. B and the bottom is positive 5. Look for two numbers that would multiply to negative 24, add up to 5, and the trick would be negative 3 plus 8. Now we can split the middle and go 6x squared minus 3x plus 8x minus 4, remembering that we could interchange those two terms in the middle. Group the first two, group the last two, and the first two have a GCF of 3x, and so we're left with 2x minus 1. The last two have a GCF of positive 4, and we're left with 2x minus 1 again. Then we put the same in one parenthesis, and we put the leftovers in the other, 3x plus 4, the outsides. And now we set each of these individually equal to 0. And as we solve these, we end up getting x equal positive 1/2 when we add 1 and divide by 2, as well as x equals negative 4/3 when we subtract by 4 and divide by 3. Now we move on to the next page. As we look at number 9, and we notice actually throughout this whole page that it is not in standard form now. It is not set equal to 0. So we have to set it equal to 0 by first subtracting 5x, moving everything to one side. Typically, I like to move everything to the left because that's what we're used to, but most importantly, I like to move it so that way my ax squared term is positive. We want that ax squared to be positive when we start factoring. It makes our life much, much, much easier. So I'm going to subtract 5x and get 2x squared minus 5x equals 0. We don't need to make the x because there's actually a GCF here, and that'll all we'll do for factoring is a GCF of not x, but actually not 2, but rather just x, and we end up getting x. So I'll try that again. All sorts of mistakes on this problem. 2x minus 5 equal to 0. That is done factoring inside the parentheses, so we're going to go ahead and set x equal to 0, and 2x minus 5 equal to 0, and as we solve each of these, we end up having the first one already solved, convenient, add 5 and divide by 2 in the other one, and we get 5 over 2, or 2.5. Number 10 here, going to subtract x squared to each side. It combines with this like term, and so we end up getting 6x squared plus 8x equals 0. Look for a GCF. There again is one. This time it's 2x, and we're left with 3x plus 4 equals 0. The inside is already factored as much as it can be, so we go ahead and set each equal to 0. 2x equals 0, 3x plus 4 equals 0. As we do that, we can go ahead and solve by dividing by 2 and get x equals 0, and subtract 4 and divide by 3 in the other one, and we get negative 4/3. Moving on to number 11. We'll subtract x squared and add 1 to get 2x squared, just x squared minus 49 equals 0. Two terms, no GCF. We do look for a difference of two squares. We do have one. X times x is x squared. 7 times 7 is 49. So we have x minus 7, x plus 7 equals 0. Set each of these equal to 0. Solve them by adding 7 and subtracting 7, and we could do x equals 7, x equals negative 7, which remember you could write if you would so choose, as x equals positive negative 7. Number 12 here. If we subtract 81 and add x squared to both sides, we end up getting 4x squared. If my pencil will choose to cooperate with me. It's writing in places I'm not writing, so that's neat. Maybe it'll full operate. We get, well, as I mentioned, 4x squared minus 81 equals 0. Two terms, there's no GCF, we check. These are a difference of two squares, 2x times 2x, and 9 times 9. And we end up getting 2x minus 9 and 2x plus 9 equals 0. Set each of these equal to 0. And now we have adding 9 and dividing by 2, positive negative 9 over 2, or we could list it as 9 over 2 and negative 9 over 2, or positive negative 4.5. Number 13, if we subtract 80 on both sides, we get x squared plus 2x minus 80 equals 0. No GCF. Go ahead and make the x since there are three terms. Anytime there's three terms, you do want to make the x. We have negative 80 on top, as we do 1 times negative 80. Positive 2 on the bottom, because b is on the bottom. Two numbers that would fit the bill. Well, that would be negative 8, positive 10. And the factors of this, since we can use our shortcut because it's 1x squared, when that happens, is x minus 8 and x minus 10 equals 0. Set up our two equations, we get x minus 8 equals 0, x plus 10 equals 0. Add 8, we get x equals 8. Subtract by 10, and we get x equals negative 10. Number 14, we subtract x and subtract 4 to get everything to one side, and we get x squared plus 10x plus 25 equals 0. There is no GCF, but we do have three terms, so we're going to go ahead and make the x. And 1 times 25 is 25. We have 10 on the bottom, and we have 5 and 5 on the sides, and we'll have x plus 5 and x plus 5 equals 0. At this point in our learning process, we want to not write them as x plus 5 quantity squared, like we learned we could, or we reminded ourselves we could during our factoring refresher. And the reason why is because we're going to recap the method that would use that, strategy or that tactic. We're going to recap that method in a future class. But for today, we're just going to leave it separate because that's going to play more in line with the method we're recapping today. So we set each of these equal to 0, and the neat part is if you set one equal to 0, you essentially set them both equal to 0 because they're going to give you the same answer. And so we subtract 5 in each of them, and you can write x equals negative 5 once. You can write it twice if you want. It's the same thing regardless. So you can write it once, you can write it twice, you can write it once and call it a double root because it's the same root, 0 solution twice. So that's optional. If you want to write the dr, great. If you don't, that's fine too. If you're going to write x equals negative 5 twice, that's fine, cool. If you want to write it once, that's fine, cool. It truly is fine whichever one you do. That'd be the type of problem where when we were graphing last class in 4.1, where it touches the graph exactly once at x equals negative 5. Anyway, moving on to number 15. If I subtract x squared and add x to both sides, I end up getting x squared minus 8x minus 65 equals 0. I go and make the x and I get negative 65 minus 8, or negative 8 on the bottom, and try to figure out the two numbers that would do the trick. And it'd be negative 13, positive 5. I can do the shortcut because it's a 1x squared, so I get x minus 13, x plus 5 equals 0. Set each of these equal to 0. Then as we solve, my blue one didn't want to write very well, I suppose, at the end. There we go. And I add 13, I get 13. I subtract 5, and I get negative 5. So those are my two answers. As we look at number 16, we would need to subtract 2 and add 3x to get everything on one side. So I get 4x squared plus 44x plus 96 equals 0. Thankfully, there is a GCF here of 4, so we take out the 4 and we get x squared, not parentheses, x squared plus 11x plus 24 equals 0. And remember, if you would like, you could divide by 4 here as well at this point. And to get rid of the 4 there, I'll just leave it there for now. So we have 24 at the top, 1 times 24, 11 at the bottom, because we're working on what's inside our parentheses. If you wanted to do what was outside the parentheses, or originally, you could do that and do 4 times 96 at the top, but those numbers get quite big, and I'd rather not deal with that. So instead we have positive 8, positive 3, or positive 3, positive 8. The order doesn't matter. We can use the shortcut, thankfully, because it's a 1x squared, which is quite convenient. So we have 4 times the quantity of x plus 8 times the quantity of x plus 3 equals 0. Setting each of these equal to 0, we could say 4 does not equal 0 and dismiss that one, and then move on to x plus 8 equals 0 and x plus 3 equals 0. And this results in x equaling negative 8 as well as x equaling negative 3. On to number 17 here, we would subtract the x and subtract the 21 from both sides to get everything on one side. And I do once again prefer moving everything toward my ax squared term to keep that positive. And I get 2x squared minus x minus 21 equals 0. There is no GCF, so I will not be able to use my shortcut this time because it's a 2x squared instead of a 1x squared. And at the top I'm going to have negative 42, at the bottom I'm going to have negative 1, and negative 7, positive 6 do just the trick. So I'm going to have 2x squared minus 7x plus 6x minus 21 equals 0. Group the first two, group the last two, look for GCFs. The GCF of the first is x, and we're left with 2x minus 7. The GCF of the second is positive 3. Oh, I did my parentheses too early. And we're left with 2x minus 7, the same thing, which is good. It's a good sign. So we put the 2x minus 7 in one parentheses, and we put the rest of the numbers in the other parentheses, aka the x plus 3. And now we set each of these parentheses equal to 0. Then we solve by adding 7 and dividing by 2 and get x equals 7 over 2, or 3.5, and subtracting 3 and get x equals negative 3. Moving on to number 18, I would subtract x and add 9 to get everything on one side. I get 4x squared minus 12x plus 9 equals 0. There is no GCF of all three terms, so I go ahead and make the x, and 4 times 9 is 36, and I end up getting negative 12. And I had to think of what are two negatives that would multiply to 36 and add up to 12, and the answer is 6 and 6. And so I have 4x squared minus 6x minus 6x plus 9 equals 0. And as I group the first two and the last two together, I notice the first two have a GCF of 2x, and I get 2x minus 3. The last two have a GCF of negative 3, noting that we want to make the second parentheses start positive, so we can match. And we get negative 3 outside, and we get 2x minus 3 inside, and hey, those parentheses match. And so one of our parentheses would be this 2x minus 3. And as we look at our other parentheses where we put the leftovers, it's also 2x minus 3. They happen to be identical again. And just like I mentioned up above, we don't, on number 14, we don't want to write it as quantity squared right now, because it's going to kind of mess up what we're trying to do with solving by factoring. And so we want to go ahead and just set each of these equal to 0, which once again you could technically just set 1 equal to 0, because you're going to get the same answer twice as long as you do your math correctly each time. And adding 3 and dividing by 2 gives us 3 over 2, which once again you can choose to write twice, you can choose to write once, you can choose to write double root next to it or dr next to it. I'm good with any of those options. There are a couple more pages in this section of notes, the ones that are landscape orientation, with the table that we're going to be skipping. So we're going to be skipping this page once it loads, as well as this page. And so that means that wraps up our Unit 4.2 notes for Algebra 2.